Thank you. All right, great. It's nice to be here. I came here maybe 9 years ago, and I was probably sitting somewhere in the back, and I have to say I enjoy the lectures when you can come and ask questions. But I wasn't, yeah, but I was not that kind of person at the time, and I had to go back and do the hard problems myself without asking questions. So I would encourage you to come and ask questions, because the homework problems that I've been thinking on, if you avoid them now, you will encounter them at later times in your life. So these kind of things just keep coming back to you. So you try to push them away, but at some point you just need to deal with the calculation. Okay. So the title of the lecture is Amplitudes and Gravitational Waves. So this is a very unfair position I was put in, because obviously I cannot cover this vast topic in 3 lectures. So this is extremely complicated to actually go through and summarize, especially since the field has kind of blown up in the last five years or so. So I will just try to make 3 points, like 3 key points, and that's all I'll do. So each of these sort of topics has one sort of kind of upshot. It has one upshot, one takeaway message that you can just go home and think about it. And today we will start with this idea of what it means to observe something asymptotically, what it means to essentially do an experiment. So in physics, there are two kinds of observations. So the first kind of observation is, you just have enough precision in your detector, and you will see some kind of phenomena, and then it looks like there's some pattern there, so you want to explain that pattern, but you don't really have a grasp of the theory, right? So it's more like a question mark. You have a theory that's developed enough to tell you something about it, but not the full precise phenomena. So there are parts of the theory that are kind of unexplained, and so you kind of have these anomalies, right? So it happened with, I don't know, quantum mechanics was developed to explain black body radiation. At the time, classical mechanics was not able, or field theory was not able to explain all the peculiarities of black body radiation, right? And so we had to develop a theory for that, to explain these anomalies. Some other times, so that's like the anomalies, right? Some other times, we have a theory, and that theory is precise enough that allows us to make predictions even before making the experiment, right? So some other times we have predictive power, right? And in those cases, you just turn the crank, you know exactly what you're going to see, and you just want to confirm. And this kind of prediction was kind of at the core of 17th century physics, because people believe that given initial conditions, right, the initial conditions of a system, you could predict the final state at any time, at any point, right? It was kind of obvious from the determinism, the Newton equation, or the Laplace, Lagrange, whatever. All these guys were just making the point that you can make strong predictions just based on these initial conditions. But then we learned, okay, there are these anomalies. This cannot be described by this determinism. And so quantum mechanics takes in. And then we learned that in quantum mechanics, we cannot really accurately predict the final position of a system. What we can do is we can sort of have probabilities, right? So we have these probabilities that look like expectation values, right? So you take some observable sum operator, and then you just look at this expectation value in some state. And so all that we can do is we can prepare a state in certain initial condition, and then we let it evolve with some evolution operator. And so at some time t, we just measure the state, and we have some conclusion of the interaction. So that's sort of the most like deterministic thing we can do. Okay, so determinism is dead, but instead we have something that allows us to prepare initial state, evolve it, and then have some expectation value. Okay, but in particle physics, we don't exactly do this. I mean, in particle physics, we think of some blob, where the scattering occurs, and then you throw in some particles, and then something will come out if time goes in this direction. So there is some kind of initial state, and there's some kind of final state. So it doesn't really look like this expectation value, right? So I'm telling you that the things that we can measure actually look like expectation values, where we prepare initial state. But in these scattering situations, we take some initial state, we evolve it, and then we project it to some final state, right? So let me just be more precise by defining what the scattering amplitude, or the S matrix, means. So the S matrix is defined by the overlap between some final state, let me call it phi out, and some initial state called phi in. Okay, and this is given by, so phi out is kind of the evolved version of phi in, right? And then you just project this on phi in, right? And the S here is just what's happening in this blob. So you can think of it as the limit where t and t prime go to infinity of the evolution operator. Okay. So this is kind of the sort of imprint of sort of evolution here. We start with an initial state, then we evolve it, and we get a final state. This in here just means that it's evaluated in the same Hilbert space as the incoming particles, but it has different momenta, right? So if we have some labels here, P1 and P2, this would be different momenta. That's what this prime means. Okay, but actually in real life, we don't measure these things. What we measure is cross sections. So I just want to sort of advocate in 1 minute why the cross section is more similar to an expectation value of a wave package than to this in-out observable. So imagine I take this. Let me just define it as the amplitude, and then I take the conjugate of the amplitude, but I sum over these phi primes. These phi primes are some outgoing final state. Maybe the label in is a bit, let me just not call it in for now. Let me just label it as phi goes to phi prime. So I'm just going to sum over phi prime in certain region of a phase space. Let me just call that region delta. And usually that involves doing some integral or some sum. And what you get at the end of the day is something that looks like your phi, the original one, S dagger, just because you conjugated this, S from the first one, and psi. But there is something here. Let me just call this something coming from the sum over psi prime, and depending on the region of phase space, n of delta, right? So n of delta is just counting how many psi primes I am summing over. And presumably, if I sum over all possible psi primes, so if I include all possible scattering processes, I should just get 1, which is kind of the unitarity condition, right? So I imagine that I consider all possible psi primes. And so I have these internal states, which I'm summing over. And I just want to understand the probability of a particular psi prime being generated where this psi prime is in this region of the phase space. OK, so this is what you usually call the cross-section. I mean, we have to divide it by the flux, but let me denote this proportional. This is not an amplitude, but it's exactly the probability that we measure. And you can see in this form, I can recast it as an in state, because these two are just states that I'm preparing. And so it doesn't matter what kind of preparation I put into states. It can be two particle incoming state. It can be a thermal state if I just average over the momenta with some thermal distribution. But at the end of the day, what I'm seeing is an expectation value of this state. And so this is exactly what quantum mechanics tell me I can measure. Yes. Yes. Sorry, is that a question? Yes. Yeah. Yeah. OK. So that brings the question of what else can I measure that's not just these cross sections, right? Maybe I can measure more interesting observables, just using this philosophy. Where's the yeah. OK. Yeah. Yeah. M's have psi primes, right? But I'm summing over these psi primes. So if you want the explicit definition of n, is the sum over a region of the phase space of the phase space measure, right? Of these psi prime states. Well, yeah. Okay. Yeah. What I mean by phase space measure is literally, if you want, the integral over psi prime. Yeah. This is what I mean by allowing you allow certain internal state, and then you integrate over the phase space of this internal state. This is what psi prime is. OK. Yeah, exactly. And that would be the fact that if I integrate over all possible states, not just 3 particle, but n particle states, right? The probability of that process has to be 1. So this is the fact that if I integrate over the whole phase space, S dagger S is 1. But if I integrate over just, say, 3 particle states, then I have a definite cross-section, which is what I want to measure. Yeah. OK, so let me just use this as a motivation to define other kinds of observables. So here you can think of this as being the expectation value of n. And in a similar fashion, we can measure different observables by looking at the scattering processes that generate them. So here I'm defining you what this expectation value is. So some examples of operators we will be interested are in particular in the gravitation, what we call the gravitational wave scattering. Scattering is first momentum or impulse, if you want. So we want to measure some operator p mu. We want to measure angular impulse. this being the angular momentum operator. We want to measure a waveform. Which just means what is the expectation value of a particular field, in this case, the gravitational field, h mu nu. And we want to measure, sometimes we want to measure flux. We want to measure these particle numbers, right? We just want to measure the probability that we generate certain states. So we can measure many things using the expectation values. Okay. This should surprise you because we started from this intuition of classical mechanics. We have the initial conditions. Here, those initial conditions are encoded in our state. Our initial state is prepared in some way. We are at the LHC with these big magnets, and we just shoot these beams of particles with determined momenta. So we prepare these initial conditions. But we also need some kind of evolution, right? So here it's not obvious. Well, maybe if I write it like this, it's clear there will be some evolution operator. But you may ask, where are these equations of motion, right? So the equations of motion are the ones that determine what the evolution is in classical mechanics. And here it looks like it's somehow encoded in the S matrix. So I just want to give you one example, which is, I think, the first example that anyone should do in this business, which is to understand how the equations of motion are encoded in the S matrix. And then this will look a bit disconnected from this, but then we will see it's the same. So let me just call it from classical equation of motion to the quantum one. Okay. Okay. So usually in Newtonian mechanics, you have some momenta, and then there's an evolution of that momenta. So I'm thinking of, for instance, some kind of process where I have two particles, mass m1 and m2, and then they have some relative momenta between themselves. So these are P1 here, P2 here. And you just want to see how these relative momenta evolve. If they have the same mass, this would be sorry, maybe we should consider the same mass situation. It's a bit easier. Okay, so classical mechanics tells you, okay, that's very easy. You just have a potential in this case, the binding energy of this system. So you just integrate from the initial time to the final time. Sorry, this is the total variation of momenta. You just integrate from your final time to initial time the gradient of your potential. Right, that's just Newton. And then, so that's the classical equation of motion, but then you go and learn from quantum mechanics that these potentials that control the interaction between these two, as we also saw in Ricardo's lecture, are interesting. They can be represented as the Fourier transform of an interesting object. So let me just write the object in precision details. It's a 4m squared here. So this object that goes in here, you learn from just scattering particles in quantum mechanics that can be understood as a 4-point amplitude. Okay, so this is like when you derive this Coulomb potential from QED, you imagine that you have these two electrons, if you want, exchanging one photon. And then after you Fourier transform, so this gives you 1 over q squared, but you Fourier transform it, and then you get 1 over r. So this is called the Born approximation. Okay. And so now you have these two questions. One is classical, one is a Born approximation of quantum mechanics, which is also called the correspondence principle. And then you just implement these two equations together. You put the potential in here, and then you see what happens. And this would be your first homework. It's just to show that the momentum deflection will be given by essentially the same formula, but there is an insertion here coming from this gradient. And instead of oh, sorry, I forgot one little point. To solve an equation that looks like the derivative of momentum equals something, we need the initial condition of the position and the initial condition of the momentum, right? So I can call this my initial velocity, but the position, I'm just going to say, is described by this impact parameter. And so what this is saying is that this system is determined by the impact parameter of the two bodies as they scatter, and this is essentially the angular momentum. But this is an initial condition, right? So my momentum deflection is going to depend on this initial condition, and this is exactly what's going to enter this Fourier transform. And then you have QP. These are the relative momenta, and this is the momentum transfer, Q, and then A4 of Q. And I omitted some factors which might be important. Let me use 4m squared. Okay. This is a 3-vector. Okay, so what this means is, okay, again, I'm just determining the initial position, which is my impact parameter. Then I Fourier transform my amplitude from Fourier space to the impact parameter, and that is the answer. So there's an interesting delta function here, which tells me that the relative momentum is orthogonal to the. So if you imagine my momentum is in this direction, the impact parameter and the momentum transfer are Fourier conjugates. So roughly, this impact parameter is 1 over the momentum transfer, but they are going in this transverse direction, and this condition just tells you the kinematics are consistent with that. Okay, so this is something that you can do in classical mechanics, and then it uses the Born approximation. How is this related to the expectation value? This doesn't look like an expectation value. It looks like, again, the same process where we have some kind of final state, psi prime, psi, psi, because we're scattering something from initial to final. But the answer only depends on initial, only depends on the impact parameter, and essentially that's it. Okay, so to sort of reconcile these 2 points of view, what we're going to do is we're going to impose the condition that this psi is classical. And so what does it mean for psi to be classical? So that now we're talking about the classical limit of psi. Okay, so what does it mean to psi, for psi to be classical? What does it mean for psi to have momenta P1 and P2? So roughly, my psi has to have something to do with P1 plus P2, right? But we also want the position of psi to be determined, right? So we want psi to have determined position. And we learn in quantum mechanics, you cannot determine the position and the momenta at the same time. So we have to do something with P1 and P2, which comes down to a smear P1 and P2 over the phase space. Okay, we have to make them kind of wave. So there is some wave package, if you want, that has something to do with P1. Let me just call it P1, P2. And so this is not exactly a fixed momenta state, but it's smeared. So you can imagine that it's centered around the classical value, but it's not determined. And so what we can determine with certainty is this impact parameter, because this just separates, this just tells us the separation between these two wave packages. So you can convince yourself that that amounts to a phase where we insert the impact parameter, and we just integrate over P1. So this is a state. This is a state of fixed impact parameter. Okay, and for this to be a classical wave package, what you need is you need the impact parameter to be large enough so that this looks like a particle. So if there's a size of the impact parameter, let's say the particles are very, very far away, then you don't really see the wave packages. You see a localized point. So that means that the Compton wavelength, which is essentially the dispersion of this object, so the Compton wavelength, which is h bar over m, has to be small as compared to the impact parameter. Okay. So this is what, so essentially you have two wave packages. One is at momentum 1. The other one is somewhere here, momentum 2. And what's going to happen is that we're going to scatter these particles. We're going to scatter these particles, and then they will come out with momentum P1 plus Q and P2 minus Q, right? Just from momentum conservation. And so the scattering is essentially going to deviate the particles from their straight line trajectories, but it's going to deviate in a way that it doesn't change the classical interpretation. So these wave packages will slightly shift around some distance Q, but this Q will still keep them sort of in this on-shell state. Okay, so this is just a definition of the classical limit. Now let's try to compute the actual formula, which is the impulse. Sorry, just to make one point, the actual classical limit, I didn't really mention how to analytically define it, but it has to do with the fact that Q has to be sort of quantum fluctuation in the trajectory of these particles. So that amounts, and it can be also seen from the Fourier transform, that what you have to do, well, we will see it right there, but what you have to do is you have to rescale Q by h bar Q. So that means that this fluctuation will be small, and we can still use the same wave package for the in and for the out state. So now h bar is going to 0. So that means that approximately these wave packages are still in the classical. We will see this in a second. So let me just write this formula where I take time to infinity, right? So now I'm going to take this O to be the evolution operator, which is S dagger. And I want to measure the deflection of momenta. So I'm going to measure my final momenta in the particle 1. And so this will be my final momenta, right? And then my initial momenta will be just the same measurement in the initial state. OK. So I remind you, this is the evolution operator, which we also call the S matrix. Just to remind you what this thing is doing. It's just evolving the system. So this is what I mean. This is what I mean by this being the final state and this being the initial state. OK. So now we learned from quantum mechanics that this has an identity part, which is the trivial part, plus an interacting part. So if there was no interaction, obviously the evolution would be trivial. So you should think of this T as being the actual amplitude. It carries a power of whatever the coupling is. In this case, it can be G Newton or the QED coupling. So we just subtract these two expressions, and we write S I plus IT. And we get the following identity. This is due to KMO C, which is this P1 T psi plus psi T dagger P1 T. OK. This is a vector, so you have to put a vector index. OK, so this is just algebra, right? I just inserted S equals I plus IT. There will be a quadratic term, which you can write as a commutator, and there will be a linear term, right? Now, we need to interpret this physically. We try to understand what's going on in this sort of in-to-out process, right? So I was telling you, we started from some wave package of momenta P1, P2. Then we evolve it with S. The non-trivial part of S is called T. So let's try to imagine the process. I start with this wave package. Suppose it has two momenta. Then there is some T, which is this scattering situation. And then at the end of this T, I measure this P1, right? What it means is that I just read off the momentum of the particle 1 after I scatter it, right? So I just multiply, if this is my scattering amplitude, I just multiply it by P1 in the initial state. OK, in the other case, there is another term in which I first, sorry, let me just call this P1 prime. Right, this is the momenta of my particle 1 after I scatter it with T. There is another term in the commutator in which I first measure the momenta of my wave package in the particle 1, and then I scatter it. And then I have to subtract these two. Right? So this subtraction between P being first or after the scattering just amounts to because the S matrix is the same here, it's both in both cases T, and this is just a number. It amounts to multiply the S matrix by the momentum transfer, Q, which is defined to be as P1 minus P1 prime. And then all I have to do is I need to integrate over whatever wave package I'm considering, right? So I said this is a wave package now. And I need to make sure that whatever comes out is still on shell. And I think I forgot to put that here. Obviously, you only care about the wave packages. I mean, it's implicit here, but you only care about the two particle states which are on shell. Yes. And if you want, also incoming. Yes. So I need to make sure that after the scattering, this is still true. So I'm just trying to simplify the whole calculation in which you actually take 2 copies of that gigantic integral and then put it here. But this is exactly what's going to happen. So the final answer of that process, let me just call this I'm just going to call this the I1 term, and this is the I2 term. And we're going to discuss I2 in a second. The final answer of this I1 is you integrate over your phase space, P1, P2. You make sure that P1 and P2 are on shell, right, with the appropriate theta functions. You need to allow for the scattering of P1 goes to P1 plus Q, and P2 goes to P2 minus Q. This automatically satisfies momentum conservation, and which is part of the S matrix. So what you're left is the amplitude, P1, P2 goes to P1 plus Q, P2 minus Q. You need to insert a momentum transfer just from the formula. And then you need to Fourier transform. So remember, when I integrate over these 2 momenta, I have to Fourier transform with respect to the impact parameter. So that will still be true, except that there will be one Fourier transform coming from each side. So there will be impact parameter of P1. Then there will be impact parameter times P1 prime. Right? I'm just putting those 2 integrals together. So the phase that you get, it just amounts to B dot Q. And then all that you're left with is just some wave functions of P1 and P2. Okay, it's a big formula, but I would like you to, I'm sorry, I just forgot the key detail, which is P1 and P2 have to stay on shell. Right. So let me just write it. Let me just write it in the more explicit way, which is P1 plus Q squared has to stay on shells. Sorry, I forgot the masses here. P2 minus Q has to stay on shell. Okay. Okay. So it's a big integral. But now what we have is we have the initial particles on shell, the outgoing particles on shell. So I hope you convince yourself that that comes from 2 copies of that integral. We resolved the phase space integration over the final particles because we have momentum conservation, right? So the P1 prime, P2 prime are fixed by the fact that there is a momentum transfer. Sorry for, yeah. There's a momentum transfer which deflects them by Q. And so that resolves the P1 prime, P2 prime integration. We are left with this important factor, which is the fact that the momentum transfer is conjugate to the impact parameter. And remember, the impact parameter is the same in both cases. This is what it means to have in. And we are left with some wave package times the amplitude. Okay, so there are many things here, but how to see that these formulas are the same is just the fact that this 4-point amplitude is the integral over the wave package I'm sorry, I keep forgetting the masses here, of the full scattering amplitude A4, P1, P2, Q. And these delta functions, if you work them out, will become, one of them will kill one Q integral, and the other one will become, I have a D4Q here, so I have one of them killing D4Q, one of the components, the other one will become this one. But this is the formula that I wanted to emphasize, which is the fact that this is not really an amplitude, but a smeared amplitude over the initial momentum. And it's smeared in a way that we try to make it classical by implementing this notion of wave packages being localized. Okay. Is there any question about that? Because I'm going to discuss the term I2, which is slightly different. Okay. So this is what I1 means. So what does I2 mean? So I2 means to have 2 copies of the amplitude. So when we have 2 copies of the amplitude, we usually call that a cut. And I will give you another explanation of why cuts have to exist. You can see it in the Born expansion, in this Born approximation. There will be terms that are quadratic in the potential. In this case, this is quadratic in the amplitude. But they have to be there to correct. These are corrections to the Born approximation. So this is a cut term. Okay, so I could write it explicitly. Let me just give you the picture. So I have an amplitude. Again, the same initial momenta, P1 and P2, right? Now I scatter that P1, P2 with some operator T. But I generate certain states. So let me just, I eventually want to measure P1 deflection. Let me just denote it like this. So I will generate massive particles, but I will also generate massless particles. And let me just call this massless particle R, or X, sorry. And this massive momenta W1, W2. Because I generate an extra massless particles, then I don't have momentum conservation in the same way I had in this first term. Here I can just say this is P1 minus Q. Here I cannot just say the same because I have an extra particle. And the other copy of T just comes next. Okay, let me just draw it, sorry. Let me just draw it like this. P1 plus Q. Okay, and what I'm going to measure is this momenta in between the two scattering processes. So I'm going to multiply this process by W1, which is the momentum of the particle of mass 1, if you want, or like the P1 particle. So the formula, after I expand it, tells me to multiply these two amplitudes, have an extra particle x, which I integrate over. So I have to integrate over the phase space. I have to integrate over the phase space of P1, P2. Again, the same. I have to integrate over my W1 and my Q. Then I will have the same impact parameter. And I just insert a copy of W1. And then I have to integrate over x. Usually we call this the sum integrate. Okay, so we refer to this as the I2 term. It has a Lorentz index, and then we can ask, so this is the I2 for P1, and there will be a term for P2, and then you can check that I1 plus I2 gives the expectation value of the radiated momenta, which is the momenta of x. Just by the fact that here W1 plus W2 add up to k of x. So we imagine that W1 and W2 are internal momenta. We sum over them, and sorry, I should briefly mention that this is the actual formula. Yes. So we add up over all possible internal momenta, and then there is one graviton or photon that's being radiated, and this amounts to the conservation of that radiation. So this is important because the first term that we discussed didn't have any radiative contribution. So you see here there is no massless internal state. And this just amounts to the fact that radiation only enters at quadratic order in the amplitude. So this is a very important fact. In the post-Minkowskian setup, if you are familiar with the post-Minkowskian language, which I think was described in Ricardo's lecture, this will be an order G cubed. Because you have roughly speaking, you have one G from propagators, but you have two Gs from the amplitude. Okay, so these are just the two terms, which will be very important. They will show up over and over in every calculation we discuss. So what I will do is I will just derive them from a different way. So maybe if you find this slightly complicated, then we can actually discuss a different way of deriving these terms, which is even more complicated. But it shows a little of what's going on behind the curtains. So I really didn't have an explanation of why there would be a quadratic term, right? It sounds like just from this formula, there is an interaction operator, and it's just the fact that you're evolving it from both sides gives you this quadratic term, which is very complicated. But it doesn't really tell you why you need these quadratic terms, and you will see them in the Born iterations. All of these quantum mechanic perturbation theory have these quadratic terms. But there is a very nice explanation of why they have to be there. And it's not this one. So that's exactly what I want to discuss now. Okay. So now we come to my favorite part. Which is called the informalism. Okay. Informalism. Okay. So let me just sort of step back a bit and try to discuss this calculation in terms of Feynman diagrams. So if you want to, mathematically and do these Feynman diagrams calculations, you have to make sure that you're using the right I epsilon prescription. And so when you write the propagator, right, you have to do, for a massless particle, for this X particle there, you have to make sure that you are doing k squared plus I epsilon, right? And not k plus k0 plus I epsilon squared, right? This is what the Feynman diagrams are, right? The Feynman diagrams are built with k squared plus I epsilon all over the place. What this gives you is the Fourier transform of these time-ordered correlations. Right? This is how we compute Feynman diagrams with the pad integral. Every time you put in a pad integral, you immediately become time ordered because the pad integral needs to know which guy to integrate first. Unlike so, in classical physics, we go to field theory and study electromagnetism. We are told, oh yeah, you have to respect causality. And so this is like the whole thing, determinism thing again. So we have initial conditions. We want to evolve them. We need to respect causality. We cannot evolve from the far future, right? So this is what this I epsilon means. And what that is you need to use these retarded propagators, right? This is what Ricardo was emphasizing yesterday, which are causal, right? So you have some theta function, okay? Well, it's integrated over the phase space, right? So that's what the cat means. So the cat means is on shell. Yeah. Is that what you mean? Yeah, they cut. Yeah, the cut means they go on shell. So yeah, this means it's on shell. So you integrate over the on shell phase space. Okay. This is amazing formalism, and actually, this is a precise formula that people can use to compute all of these things because I was just showing you all of these expectation value of operators can be expanded in this way. I just did the momentum, but it doesn't give you much intuition of what's going on inside these blobs, right? So all of these blobs are Feynman diagrams. They are computed with this guy, the time order correlation function, the time order propagator. But at the end of the day, we want to use it for actual measurements, and we learn from classical mechanics that we have to do measurements with the retarded propagator. So this is kind of the big puzzle that is not at all obvious from that picture. Okay, so but somehow it gives the same answer. Like somehow this calculation agrees with the expectation that we have from solving the equation of motion. As I show you, so I show you the first case in which you compute this delta p. Yeah. So this delta p, right, is exactly the same that you would compute from the equation of motion. Yeah. Okay, so maybe did everyone hear that question? No. So the question is in the case of a binary system, we expect all the contributions coming from potential modes, right? And that's the case here. If you imagine that this amplitude is just a Coulomb amplitude, right? That's a potential mode. But there are dissipative contributions to the scattering. And so those are related to the cut, which are the imaginary term of the amplitude, which is exactly these radiative modes that Ricardo was mentioning. So there will be conservative part coming from these terms, but even here there will be some radiative contribution. But roughly speaking, this will contribute to the radiative part. So it won't matter if you just care about conservative sector. But we want to compute everything. So we want to compute, when we compute a momentum deflection, we care about energy that's being radiated away. So we actually need to understand the dissipative part. Okay, so this is the puzzle, right? So these two things somehow are consistent. They compute the same thing. And then let me explain roughly how these two objects are essentially the same, or they are different boundary values of the same object. And that object go by the name of Schwinger-Keldysh contour. Okay, so what does that mean? So imagine you have a path integral along the time direction, right? So you imagine that you have some time direction, and then you have infinity here, minus infinity here. So you insert these operators, right? So phi x is here, phi y is here, and then you perform your, I just want to make it like this. So I'm going to put x, here. And then the path integral will just integrate along time, and it will naturally order the operators, right? It will first, it would put the operator that's first in time, first in the two-point function. But sometimes you want to order them differently, depending on whether they are time order or not. So what we do is we make another copy. So we make another copy of the contour. And then what we do is we call this the plus copy of the contour, and this the minus copy of the contour. And then we will put these operators in different contours depending on whether we want the time order or the retarded propagator. So let me just do it like in this case. So I have this time order phi x, phi y. And here I'm going to put another copy of phi y. So let me just call this the phi y1 in the, let me just call this the phi 1 plus or phi 1, yes, phi y, let me just call it plus. Yeah. And then let me just call this the phi y minus. So I have two copies of phi. That means like in my path integral, I will have, if you remember the formula for the path integral, there will be an action for phi 1, and then there will be an action of phi 2. Sorry, I keep changing this. Sorry, plus and minus. And importantly, there is a minus sign because we revert the orientation of time. The important point is that this is one single contour. We just like to split it into two parts, but we are kind of double covering the time integration. Okay, and we impose that as we go to infinity, the phi's have to be the same. So this usually goes by the name of our largest time equation, which is the fact that as you go to infinity, on the plus and on the minus branch, you are in the same field. So this essentially is what glues these two contours. So now you see what will happen. The path integral will order the integration, but even though this phi x can be first than phi I, because of the integral over this contour, phi x will always come in later. So it doesn't matter whether I put phi x here or phi x here, because of the fact that the contour is ordering this way, phi x will always come later than phi y in the path integral. This is a key point. So now let me give you the expression for these two boundary values. So one is the Feynman propagator, which I said is the time order propagator of phi x, phi y. This is the one we use to compute the Feynman integrals, right? The Feynman diagrams. And it comes down to the Schwinger-Keldysh ordering. So this is exact ordering, where I put phi plus x first and phi x in the plus contour and phi y in the minus contour. Sorry, my apologies. Yes, this is just standard thing. So if I don't have this retarded condition, I just don't care about the second branch. I can put them in the same branch, and I know that this will integrate in the time order way because they are both in the same branch. In the retarded case, so my retarded propagator, so let me just call this Feynman. I would put x in the plus branch, and I would put 2 copies, as I just mentioned, 2 copies of y. Let me just call it the vacuum. Okay, so this should give theta x, theta y times the commutator. Okay, so how do we see? So this has 2 terms. These 2 terms are exactly these 2 insertions. The interesting thing is that these 2 insertions can interact. So I can compute phi plus, phi minus. I will come back to that in a second. And then you can check that maybe if you put the expectation values in this way, right? So here x0 is greater than y0. Then you can get just the commutator. So you can forget about this theta function if you put the x in this ordering. Although I think in this, sorry, let's just assume that time flows in this direction. Just 1 second. And then we want to say that x0 is greater than, sorry, yes. To get a non-zero answer, we should put it in this one. So roughly what happens is that if x is on the other side, suppose x is on the other side, these integrals, there will be two integrals, but they will have the same contribution. So if x was here, there will be a side coming from this term and from this term, and they will cancel, because in each of the terms, phi x will be to the right. Okay, this is something that you can convince yourself, just to check that this is 0 when x0 is less than y0. Essentially, that these two terms cancel. And yeah, and if it's not, yeah, and if x is 0 is to the right, then there will be one term in which phi x will be first, and then another term in which phi x will be second, and that's essentially two terms. I hope I did it correct. Yeah. Okay. So this is what people have been doing for a long time when computing correlation functions, which are these objects. But now we want to compute amplitudes, right? So you may remember that amplitudes are related to correlation functions, but by something called the LSC reduction. So you take a correlation function and you amputate it. And that gives you a scattering state, right? So we can imagine having a state, phi x. We integrate it phi x, right? And the LSC formula essentially amounts to reducing that state into a creation operator by putting, essentially this amounts to putting, it's essentially taking the residue as p squared goes on shell. This is what gives the particle states. Yeah. Sorry, can you speak loud? Right. 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 So what you're referring to is the fact that we can put phi x and phi y in two different positions, which is plus and minus. And that gives us combinations of combinations of those. So combinations of those elements will become either Feynman, retarded, advanced, and so on. And usually, I think the identity is something like phi plus minus. So this will be the plus plus entry, and then there's like the minus minus entry. This will give us this will give the retarded propagator, but it's pretty much equivalent. I'm not seeing exactly how now, but this formula, the usual formula, is equivalent to the to this one. Yeah. But this is what you mean, right? Yeah. Yeah. So we're not interested in the full. So we're only interested in the Feynman case and the retarded case. So we just need two contours. We don't need 4 of them. And I just gave you what the two contours are. So that's all you need to remember, because this is exactly what's going to give us these complicated quadratic terms that I just erased, the fact that you have two contours. So the quadratic term essentially is coming from interaction between these two contours, sort of 2-point function between plus and minus. This is what the quadratic term is. So let me just rewind a little bit. So when we want to compute amplitudes, we have to amputate the final states, right? So we do that by doing the LSC reduction on this state. So we do LSC of P1 and P2. Well, this would be the two-point function. And in the case that we're interested in, we are looking at the 4-point function, right? Let me just remind you what we're looking at. We're looking at the 4-point function of S dagger S, P1 mu S, right? Psi. Yeah. Okay, so this would be, again, we're going back to momentum transfer. And if we care about radiation, sorry, if we care about, say a waveform, maybe I should do this example too. If we care about a waveform, what we will insert here is just expectation value of certain operators. So we want to create, some radiative state, this on-shell state of energy k. So we just look at the expectation value of the energy k insertion in this psi state. Okay, so this 1 second. Okay, so we want to compute this from Feynman integrals, but we can also compute them from the Schwinger-Keldysh formula, and we can show it's the same. So in the Schwinger-Keldysh formula, what we will do, so here's the rule. What we will do is we will put the operator that we want to measure in the second branch, as if we were computing just normal Feynman diagrams. So we will put this operator in the second branch. So we will put this operator, let me call it, well, A dagger is a good name, but I think H would be better, just to make the point that this is going to be a waveform. So we will put H mu nu in the second branch. And then we will put one copy of each of these external states in each branch, right? So these operators are going to be time ordered, sorry, ordered in a causal way. So we will put one copy. Let me call it phi dagger. Phi dagger. So we will put one copy on each branch. So what this amounts, let me just write the actual expression, and then we can see why it's the same. So let me just put the H in the second branch. So I'm going to do the Schwinger-Keldysh contour of H on the second branch. Then I'm going to have phi on the first branch minus first. So this has to be momentum x. Let me call it x1, x2, okay, this one I'm going to call x1 prime, x2 prime. And at the end, I'm going to obviously amputate. So what I want to do is I want to take this correlation function and I want to amputate it in x1, x2, x3, x4, and k, which I will call x. So remember, what amputation means is you. So I should have written it. What amputation means is that you take this position value operator, and then you smear it, go to the pole, and then that gives you the particle creation operator, which is what we need, right? This is how you take the correlation function of 4 phis into an actual amplitude. So I'm just computing the correlation function. To compute the correlation function, I'm going to use the Schwinger-Keldysh formula, which tells me I have to put 1 copy, just as I computed for the retarded propagator. The same thing happens for the full 4-point function. I have to put 1 copy in each branch. The external field gives me a waveform. I'm just going to put it on the second branch. And then I need to integrate. Yes, one more. X2 prime, sorry, it's X1 prime, X1 prime. And when you smear with this psi, what you have to do. So at the end of the day, this will be some momenta here. And then what we need to do is we need to integrate over 5, P1, P2, P3, P4, using our wave functions, right? This is exactly what we did for, and so on. So this is how you take a correlation function into an in observable. The fact that it's in tells me that I need to use this Schwinger-Keldysh contours. Now, what is the reason that the Schwinger-Keldysh contour is it's important is because this is, as I said, is computing the retarded propagator, which is measuring the response. Is measuring the response of one operator after a deformation by the other operator. So if I have some interaction Hamiltonian between these two operators, this is the deformation, is the response of this operator after this interaction occurs. So this is exactly what we do when we compute these waveforms. We look at the waveform after we look at, sorry, just to make it super clear, we look at the response on the waveform induced by the operators phi, which are the massive black holes, if you want. So just to make it super clear, just gonna write the actual, so what this is equal to, this here is just acting on H with a lot of these phi operators, so it's this nested commutator, where you generate H by acting through these phi operators. Through an interaction Hamiltonian. So this is what's called the response functions. Okay. Yes. So this is in, right? Do you agree this is in? Okay, let me just make it a little more clear. Yes, so this is an in expectation value, and all we need to know is how to compute this in expectation value from the Feynman diagrams. But in order to do so, we need different rules for this Feynman diagram. So this is what this contour is doing. If I were to just compute the usual Feynman diagrams, I wouldn't get the in functions. No, this is not a constant time. I think we should discuss this in the discussion session. I just want to finish with, I have like 0 minutes, right? Oh, I have 5 minutes? Okay. Okay, good. I still think we need to discuss this in the discussion session. But let me just finish with just the formula. So suppose I actually compute the expectation value of these operators. I'm going to have a term that involves H2 with phi 2 and all the 2's, right? So I'm going to have a diagram. When I look at all the 2's, that is just a standard path integral, right? So if all the guys are in the same branch, right, I can use my usual I epsilon. So I compute, when I insert guys here, I just look at the Feynman diagrams with this operator, right? So this is, let me just write it in the most natural way by just drawing a diagram, calling it plus. Sorry, I really apologize that I oscillate between plus and 2. These are different notes that I wrote. But maybe I think I call it plus over there. Yeah, so let me just call it plus. Yeah, I really apologize because I had different notes for these two things. But okay, you get the point. So I have pluses and minuses. So the first term of this computation will come just from interacting all of these operators in the plus counter. So this is standard Feynman amplitude. But then there will be terms in which my pluses interact with the minuses, right? So I need to tell you how the plus minus can interact. Well, it turns out that if you work it out, this is nothing but a cut. This is the cut where the particles are on shell, so the propagator is on shell, and the particles have the same momentum. So what this means is that these states can only propagate from one contour to another if they are on shell. So I need to add to this Feynman diagram computation a diagram that interacts phi plus and phi minus, and that's precisely if I have a plus diagram and a minus diagram, that's precisely another term in which I'm going to have plus minus propagators, so that means that I am in a cut. And then I'm going to be looking at, again, I'm always going to put the source, sorry, not the source, the expectation, the operator I'm going to measure in one of the branches. So I'm going to put in the plus branch. Okay, and that's why you do need these cut terms. It's exactly because you have these two copies. So you see one of them is computed with the Feynman propagator. It's a standard thing, but it doesn't give you these causal responses. To get the causal responses, you need the terms that are quadratic in the amplitude just because you have two copies. So that's all I want to say for today.
Is there any urgent question before we go to coffee break? Yeah, so the things that we got less time for lunch today since the colloquium starts at 2. So it's good that we come back here at 10:30 to resume. Okay, so let's thank Alfredo again. Start at 11, not 10:30. Otherwise, we'd have to go back in time.
What time is the what time is the discussion?
Sorry, today, since there is a
So you had some, sorry, you had some objection of the cutter, or is it
No, I was just wondering because, like in the beginning, I didn't really understand that you meant that you should cut the amplitudes precisely to get the fields on shell.
yes? That's what cat means. Cat means the fields are on shell.
Because I think at first sight it looks like a mostly conservative phenomenon, but you have the radiative contribution to it.
Right. So when we compute, an amplitude usually has real and imaginary parts. That is a fact. From the fact that there is an I in the